Kevin, thank you for speaking at the colloquium today. Without
Thank
any
you.
further ado, I will leave the floor to you.
Rock and roll. Welcome, everybody. So, how many of you have tried to build a robot? Not as many hands as I was expecting. Jeez. Whoa. Okay, can we do that again with the hands like all the way up? Have actually tried to build a whole robot. Cool. All right. So, as you might have noticed when building robots, is that you end up having to use many different tools, and the different tools that you end up having to use don't necessarily play nice together. SolidWorks doesn't know about your kinematics. Your kinematics is hard to implement on your Arduino firmware. Your firmware may or may not have any way of visualizing what it is you're doing. These things are hard, and they have many different tools for solving the narrow domains. We have electrical development softwares like KiCad. We have mechanical design softwares like SolidWorks, and we have programming interfaces and development environments like Eclipse, and so on. There are obviously many more examples of each, but that's kind of not the point here. As you might have noticed, that the fact that they don't play well means that a lot of us tend to specialize one particular area or another. And so what I've tried to do with BowlerStudio is build an integrated robotics development environment. Sort of a new thing that doesn't quite exist yet. I take a little bit of inspiration and give the tiniest credit that I possibly can to Microsoft for the Microsoft Robotics Studio. Anyone ever open up that piece of software? It was a good concept, if not implementation. And it lacked a certain amount of actual usability, which was sad considering how bold the strategy was. But the idea of integrating all the pieces was a good one. That just wasn't the right implementation. So what I've tried to do is recognize that we have some really interesting robotics engineering tools like ROS, like Arduino, and that there's actually, if you sort of imagine that as your scope, there's a big gap between them, where Arduino finishes out in what it can do. There's a big gap between that and what ROS can begin doing. And the mechanical side of things is just entirely different, a whole different domain. So what I try to ask the question is, what if we made a single development environment that can deal with these different domains and integrate the configuration space of each of them into a single configuration system that has components that are loaded for the different disciplines. So that's what we're going to be talking about today. So I coined a term because, science, coin terms. That's what I do. So we're calling it an IRDE, or ERDE, rhymes with hurdy-gurdy. The original idea is to turn the crank and the robots pop out, but I couldn't get a really good animated GIF of that, so we're just going to leave that to your imagination, which I feel like it's probably better than what I could have come up with Photoshop. The general idea is this consists of a scripting system, sharing collaboration architecture, that's Git, a visualization system so you can sort of see what the robot's doing before it's made physical, a CAD modeling system to design the parts from the same configuration space that you're using to build your robot, a robot definition format. URDF is cute and all, but is not the easiest format to describe generic robotics. DH parameters being my specific critique. I think series manipulators should be defined with DH parameters. Call me crazy. URDF disagrees. All right. A new definition it is. And of course, once to close this loop from the development side of things, a physics simulator that can simulate how this robot's going to perform in the real world, again, before making it physical. I care very much about the tight integrations. And the reason for that is so that you can have a fast development loop. When you're working on your robot, you want to be able to quickly swap out and change pieces as fast as possible, and then retest as fast as possible. So let's sort of imagine our way through the workflow of a simulated robot where you're going to change its kinematics, recad it, re-import it into a simulation software, rerun the simulation, and compare the results. Anyone actually done that loop before? Not just build a robot, but that whole design, kinematic, simulate, repeat loop? 1, 2, 3. About how long did it take you? Just one iteration of that loop all the way through. Huh?
8 months.
Woo! Right. No, we are going to see that in a matter of seconds. And that's kind of the idea of a good integrated development environment. It can take something that is, I was expecting like weeks, 8 months. 8 months, which is, in fairness, not unreasonable. It's not like, that guy, what is he up to? Yeah, that's not, I mean, nobody else was surprised by that. Why was I? What do I know that you don't? By the end of this, hopefully nothing. Okay, never mind. So the other sort of core component to understand for the BowlerStudio system is that it's JVM based, which means Windows, Mac, and Linux are directly supported. We use the OpenJDK and specifically OpenJDK 8 and a heavy reliance on Java FX. I'm so sad they ripped it out of core Java. It actually was kind of great. Nobody here to disagree with me, so we're just going to let that stand. So, where did this all come from? I, like you, was a grad student at one point. Way back in the early days of 2009, I was doing my graduate research work with Professor Greg Fisher. I worked in his MRI-compatible robotics lab, and we had quite a few different robots. We had robots that had very strange kinematics, these parallel, unparallel mechanisms, a Cartesian bot. There were quite a few different kinematic models, but he was very insistent that all of the controls have a standard high-level API. So what we defined is a system of abstract kinematics. What's the commands that every kinematic system has to deal with, no matter what? You know, set in task space, get task space, keeping track of all the fiducials and relative positions of your body. But what is generic can be implemented for all of them. What is unique to a particular robot should be only the forward and inverse kinematics. And then for systems that are defined as a collection of kinematic chains, the forward kinematics can be solved for you entirely. DH parameters doesn't afford you more than one way to solve the forward kinematic, now does it? So if you can define your robots that way, boom, half that problem is solved for you. And the other half, the inverse kinematics, well, that should be one bouncing around. Interesting. The inverse kinematics should be something that can be swapped out from device to device. Okay? Now, that architecture, the Java Bowler library set, was used in the MRI-compatible robotics lab for Greg Fisher's research work. That's where all of my, if you look me up on Google Scholar, that's where all of those publications came from, and the fact that that stack is still being used. Now, fast forward to 2016, two failed businesses in between those two. Neuron Robotics, gone. Neuron Robotics Take Two, gone. Technicopia worked great, though. He is right about that. That one worked out. Got 1 out of 3, I'll take it. Right after my second business failed, I had a sort of moment of, oh, building robots is hard, and I started identifying this problem. The 8-month loop for a talented robotics engineer is not something that an average person is going to pick up and start using. So what I wanted to do was build this Arduino-ified interface for doing robotics development. But of course it was 2009. Anyone remember what state ROS was in 2009? It was just being written and standardized. I think there were some publications, but they hadn't actually hit academia until 2010. Like the first time I really saw ROS anything was at the ICER conference in 2010. So yeah, it basically at that point didn't even exist. So BowlerStudio and ROS kind of grew up at around the same time. One of these two groups had a lot of grant money. The other one didn't. Can you guess which? Probably the one you've heard of. Now, the BowlerStudio system was specified to add scripting and Git as the first core component piece. We'll get into that in a minute, but we added the ability to call scripts and then the definition of where everything lives in its Git repository. I added a programmatic CAD system. The library is called JavaCAD. It's a fork of JCSG, which is a re-implementation of JSCSG. So it has gone from JavaScript to Java to a slightly less insane API version of Java. JavaFX has provided some fantastic 3D visualization, very, very fast, cross-platform, works on Windows, Mac, Linux. I really can't say enough good stuff about JavaFX, to be perfectly honest. We use JBullet for the physics simulation. Has anyone used Bullet? Or RViz uses Bullet. Same library, just the Java hooks for it. Again, I care tremendously about the speed of the development loop, the rate at which you can make a change to the kinematics and have that propagate through your model and simulation. And then, of course, sharing your code. Has anyone tried to publish a package in ROS so that someone else who isn't in your lab and can't directly access the source code accesses it through the normal channels? You have? What did that take? So you actually made a deb package and published it? Well, all right. So if I sit down, I'm building my ROS system, where do I get your package from? Oh. Okay. So the point I'm trying to make is saving a package to a source code, to a version control system, and then publishing it so someone else can use it. Different tasks, significantly different tasks? I don't think they should be. Something's available in version control, why can't my code simply just call it from its version control source? So, as I said before, I want the ease of use of Arduino, and I want the functional capability of ROS. Why can't I have both? Anyone got a good reason? I feel like that's achievable. When we take a look at the demo, we'll see if that happened. Huh.
So do you mean we will be able to use ROS in this framework, or is it like something, like it will be doing something similar to what ROS is doing?
Both. Both of those statements will be true. So first of all, ROS Java, it's available in Maven. And so one of the things we'll get into because of the JVM, anything that's published into Maven is a library that works with, quote unquote, my system. So I have a runtime framework that does a lot of its own stuff, which is cool, but it also means anything that's a standard Java library through the standard distribution channels are available. ROS is one of them. So I have a bunch of scripts that kick off ROS servers, ROS nodes, doing all sorts of things which I find to be not quite as useful for what I'm doing. And we'll get to why that is in a second. But yes, you can run ROS. It is not quite, definitely not first class, maybe third class citizen. It can be gotten to work, but it's not the purpose of this architecture. It would be the sort of thing where, boy, a really interesting grad project would be to make an auto URDF generator from one of these robot definitions, but it's not built in for that purpose yet. So, requirements. I really made this as a set of requirements. This must happen. Collaboration-oriented development. I said this a few times, but what this means is when you make a piece of code, I want that to be not just available to you, but available to anyone without sort of special access. If you make a repository public, somebody else can call it. If you make it private, it's yours, but it behaves within your system exactly as if it was a normal public repo. I take a sort of GitHub mentality to it. Everything is easy if you make it public. It's possible, but more intentionally friction-filled if you want to make things private. Does that make sense? Okay. I wanted it to be an integrated development environment for robots, generally speaking. It must be able to integrate the pieces and work as a standalone environment. Can work with other tools, and we'll see that in a second, but generally speaking, it must be that sort of standalone functional IDE. Also expected it to be cross-platform. robotics engineers cannot quite agree on whether Linux is the better system to develop robots on or Windows is a better system to develop robots on. But at least we can all agree Macs are terrible. It does, in fact, work on... Oh, I know. It works on your system, too. Don't worry. Despite my... Look, I have a negative opinion of Mac because I support it. Now, and the target audience is supposed to be someone who can't quite get enough done with Arduino, but doesn't really want to invest all of the effort of ROS. What's halfway in between and filling that gap between them? I would now argue BowlerStudio does. So, let's start getting into the architecture of the system itself. So, files, as the system understands them, yes, you can load a file from the disk. It is pure Java at the end of the day, but that's discouraged. The encouraged way of using files is to say they come from their location in Git. So when I load a file, I'm not saying on the local file system, the relative path to where I am is here. This is where I expect my file to be. Instead, I let the scripting engine cache the files to the disk, pull it and keep it up to date, but then access the file from directly its Git URL, branch, and then relative path within the Git repo. So it's just adding 2 layers of metadata to a relative file path. And then the scripting system uses the URL to generate a unique cloning directory for it. In this way, files are hyperlinked to each other via the Git protocol. Just for simple file access, this might be a bit redundant, but you can, in the same way, pull, commit, push files right inside your source code as part of the normal operations of writing software. The entire Git functionality is there. In fact, some pieces of the GitHub API are also there. You can look up what repositories you own in GitHub. You can look up whether or not you have permission to access a file from the GitHub. You can also create new repositories and fork repositories, as well as creating pull requests and merging them, all from the API. Basically took the 2 libraries that existed, GitHub API and JGit, and turned them into a single flatter static call with a standard cache location for all the files to live. So next up, not only does it load files, but it has file runners. Based on the file extension, it's going to load one of the scripting language or file loader pieces of code. These are modular. You can load new ones on the fly. But what are built in: Java, Groovy, Kotlin, Clojure, and Jython. Jython I specify as opposed to saying generic Python because it is the Java implementation, meaning you have all the Java libraries, but not all the Python libraries. Other files that it knows what to do with would be your STLs and SVGs. Those are generic interchange formats for CAD, 2D and 3D file formats, which are themselves generic formats. You can load an STL, you can export an STL. Once you load it, you can manipulate it, which is kind of cool. Same with SVGs. You can take a slice through the any plane on the system and turn it into an SVG. It does not use sketch and extrude the way a traditional CAD package does. It actually doesn't do that at all. It uses computed solid geometry, or CSG, as the standard modeling paradigm. Other file formats is the robot XML. It's a generic XML, but unlike a normal XML, you run it, and what it does is, as a standard static config file for your robot, it includes information about the robot, but also where to find the extra executing files for the robot and loads those as well and executes them. So running does perform an execution of sorts, or at least it kicks off an execution. If you return a file that is a tab, specifically a JavaFX tab, It'll show up in the UI. So if you want to modify your UI with additional tabs or 2D functionality and make it seem like a first-class citizen in the system, just return a tab. If you return any other JavaFX node, it'll show up in the 3D window on the XY plane or wherever you put it with a frame transformation. Okay? In addition to the built-in languages, there's a few other sort of other ways of thinking about files that you can run. Any INO file will be passed off to the Arduino system that's installed on your computer. It'll look for Arduino, compile it, and program an Arduino with the INO that you give it. Not terribly different than the standard Arduino IDE, just sort of runs it headless. You can also add new languages in line. I was working with Professor Paulus to do a domain-specific languages class, where he would have the students write a new language, then write a compiler for that language, load the compiler into BowlerStudio, and use the file extension for the new language to execute it on the fly. You can both load the language and then run it all live. The system doesn't even need to restart in order to do that. And then in terms of the way data is transferred between scripts. So when you call a script from the scripting engine, it returns an object and it takes an object. There's a sort of soft assumption that it is either object or list of object. List of object being something the system can also parse. So if you want to return a whole bunch of things, a bunch of CAD objects, a tab, a device that goes into the device manager, you can just return it all as a list. You can do list of list of list of list. It parses that list recursively, looking for objects that are not lists, and then processing them accordingly. So, this all seems like a lot. How would anyone know how any of this works? Well, of course, documentation. Documentation, documentation, documentation. BowlerStudio starts up, and the first thing it does on your computer is actually clone a full copy of my website onto your disk, because it lives in Git. In fact, you'll probably, if you look at what BowlerStudio is cloning, a good half of the code that actually runs is downloaded and cloned on the fly the first time you open up BowlerStudio. So the first time you open up, it's a little slow. Second time, everything's already been cloned. It knows to check the cache and run from there. The embedded documentation is a bunch of tutorials. I provide tutorials in the form of my favorite form of documentation, which is called spikes. Little blobs of code that completely do a thing, the smallest possible amount of code to do that thing. It's very similar to the way Arduino does their examples, but it's a little bit more direct in that you are looking at a web page that describes the functionality of a piece of code, and then if you see our little green run button here, it has already cloned it to your disk, and you can run that sample code that you're looking at. See the button next to it? Well, I should have used the not logged in as me version. If you're not logged in as me, instead of saying edit, it'll say make a copy. In which case you copy the example code, goes to GitHub, makes a fork, and it allows you to edit it right in the text editor. In addition to the documentation pages, the static documentation I provided for you, there's also a menu system that shows you all of your GitHub projects, your GitHub personal repositories, the projects all have their repositories, and all of your GitHub gists. It lists them off in a menu, and then just hovering over the listing what files are in this repo will perform a clone and then list off the files. The workspace is similar to that menu, except it's the last 20 projects that you opened. It just keeps those in a shortcut for you. So the last 20 that you've opened, they'll be quickly accessible. Otherwise, you go through the deep menu to find them. Now, what do we do with these scripts? Probably the most common thing that I do with this is CAD. I don't use SolidWorks or Fusion or any other sketch and extrude system. In fact, I do a lot of CAD for a lot of different robots, all of it in this. So the Java CAD system is based on CSG, Computed Solid Geometry. It's just another way of manipulating shapes to form other shapes. It's more common in the video game industry because it's very surface focused. Again, no sketches. Everything is a three-dimensional shape in the first place. Now, because everything that I'm doing, or most of what I'm doing, is designed for 3D printing, working entirely in the mesh is fine. We always have to remember that sketch planes represent machining fixtures. That's their purpose. That's what their job is in the CAD package to represent for you, the machining fixture of the blank part that is going to be machined out to produce the shape that you're making. CSG has no baked-in assumptions like that. So instead of being a 2.5D style CAD package, which SolidWorks, Autodesk packages all are, this instead is 3D first. Means I can do three-dimensional lofts. We call it hull. Mathematically, it's a little bit different, but same principle. You can do far more complex things far more quickly if you're dealing entirely in three-dimensional space. And the evidence of that is the hundreds of little robot bits that we see in Foisy. I also added a debugging system. Has anyone ever used OpenSCAD? It's kind of similar to OpenSCAD. So, was it fast? No. No. So I did some bench testing of operations. BowlerStudio is at least 10 times faster, and for certain operations, 100 times faster. It's a lot. It's a lot faster. If you ever sat there with OpenSCAD waiting for it to fully render, oh boy, it can get frustrating. It's a cool idea. Write code, get CAD, great. But again, there were limitations. So I wanted more. We'll see the debugging when we get to the live demo. You can go from your code. As you navigate through the window, it'll show you what objects in the CAD were created by that line of code. You can also right-click on an object, read the code, and it'll highlight all the lines of code used to create it. Open up any other dependent scripts that were called. The other nice part about this CAD system is if you have any experience programming, you already have all the skills. There's nothing special to this CAD package that you have to learn. You learn a standard CAD, you have to know where the buttons are. You have to learn where those buttons are. You have to learn the workflow to press the buttons. If you need to make a bolt hole, you have to find the bolt hole pattern widget and learn how to enter the data properly. Or use a for loop, because it's a for loop. Because conceptually, that's what it is. It's just patterning around a center. And then in addition to you actually already having all the core skills to use this, basically just an API from any programmer's perspective, I have a database of vitamins. So I use this term vitamins often. It's not terribly common outside of the 3D printing world, but what it means is a part that is not going to be printed by your robot. It is something that it kind of consumes from the outside. Or maybe more specifically, something you buy, not something you print. I've got a database of hundreds and hundreds of parts in hundreds and hundreds of sizes. And so all you have to do is say, I want this part at this size, and it uses the parametric CAD to generate that part.
You never hit a dead end when doing this kind of designing. You never hit a dead end when you did this, used CSG, as opposed to BREF in SolidWorks. For example, if I need to edit a feature that kind of cascades into other features, I just need to go in and edit a sketch. That's all I need to do.
Oh, I am way. So here's an example of where this problem shows up for that system versus mine. I have a robot cat. The robot cat has captured nuts. There's about 40 or 50 of them. We want to parametrically change from nuts to heated inserts. You can change measurements that way, but shapes, not so much. Parametric on shapes is not something most CAD packages deal with terribly elegantly. And more to the point, not only does that cascade, because it is essentially a function being called, that cascade does in fact work. Change one measurement in one file and everything that references works. I also can do those references hyperlinked across the internet, which means one person can collaborate with hundreds of people writing a component that their system dynamically links into their CAD. And if you don't want that to change on you, you can always specify instead of a branch, a commit. This commit is when it worked for me. Oh my God, I don't want a different version. And because it's Git, even if I make new changes, you'll always have the version that worked for you. So you have both the newest hotness if you want it, or a guaranteed stable, guaranteed by the hash commit itself in the source code as you use it. Does that answer your question? Good. So the Vitamin database is used as a series of components that you would add or subtract, more accurately, from your CAD models as you're designing your way through it. By subtracting parts that were previously defined with their own standard measurements, you can be reasonably sure that the thing that you buy will fit into the hole produced for it. Now, nuts and bolts, that's really easy. They're cylinders and hexagons. But what about servos? You know, what if you have to switch from a servo to a round motor? Is that like an easy change for most CAD? No. No. Very, very no. Skip one. So, what do we then do with this? Obviously, it's a robotics development environment. So, at the highest level, we have robots themselves. So, the definition of what a robot is in this system, I call the object type is called mobile base, and they represent a robot. One XML file generates one mobile base. A mobile base is defined as a collection of limbs. Limbs can have one of four types: legs, arms, steerable wheels, or fixed wheels. Heads and tails kind of fall into the arm category, which is a bit awkward, but ultimately from the kinematics and from the math, they behave the same way. The kinematic chains are defined using DH parameters. Standard DH parameters, as you understand them, are how you define this link relative to that link. And assuming you pay attention to how your transforms are defined, there's sort of only one correct way of defining any particular chain. Actually, room full of roboticists. Can anyone tell me if there's more than one valid DH parameter for a given arm or a given limb? Well, I mean, the idea being like, you can define an arm that would kind of be the same shape, but is it valid? Or is it in some way breaking a rule, which is otherwise known as modified DH parameters? The modified being the cheat, obviously. So yes, you can make modified ones in here. It won't break. It doesn't actually do that validation check, but strictly speaking, if you do it right once, there is only one.
There are like skews, like cases where actually you may have arbitrary, so like for instance, if two z-axes are intersecting, then you may take like an x-axis going one way or the other way, so on it's planar.
Well, the esoterics of this is a topic for in-depth debate. We'll get into that later. I actually am kind of curious about that. So, your mobile base has, in addition to its static definitions, hyperlinks, in the XML hyperlinks, to three types of scripts that are used to create the robot itself. A motion control script. So this is for body controllers or driving controllers. The motion control script takes is a interface that you implement, and the interface is a function that takes in a mobile base and a frame transformation and does something to it. It mutates the mobile base in some way to perform that frame transformation action. Sorry, frame transformation and time. So the script is defined by the absolute generic thing that you're doing. Take robot and move it someplace in some time. Every robot's going to implement that differently, so that isn't defined as a set of static code that you can't change. It's instead defined as a script that is hyperlinked using the XML that describes your robot in the first place. The inverse kinematics for each limb are hyperlinked in. And there are two levels of CAD script, one for the base, one for the limbs, assuming that each limb has its own CAD generator and each base, in this case there's only one, has a CAD generator as well. Okay. For hardware, there's a system called link loaders. We have 3 script style interfaces and then about 25 link types that were baked in from the old Neuron Robotics days. Use the DIO if anyone knows what that thing is. Does anyone know what that is? Wow, finally gotten over to the other side. Nobody even knows what it is anymore. Cool. So there are 3 types of, as far as you're concerned, link loaders. An HID-based link loader, a UDP-based link loader, and then an HID full motor controller. So the difference being HID-based servos, which is just a byte to tell it a position, versus an HID-based 3001 arm. So anyone who's done the RB 3001 stack, there's a full implementation of the robot in here. In fact, this is the CAD package that was used to define it, or design it. Now, once you've loaded your robot, you have a creature lab. So the creature lab is this window here, and it's sort of a color-coded, labeled XML editor that once you get down to a specific tag, it has an editor window, not just to edit data, but to live update the model so you can see how those edits change your robot. And finally, from an architecture perspective, everything that you see here that runs inside BowlerStudio can be run headless. There is a clean separation between a kernel and the UI, and you can run the kernel headless, and all the functionality for robot control can be run independently. We did some significant real-time testing with the Java Bowler stack, and further compiling the JVM jar down to a linked preempt RT real-time module. And that whole stack has been tested. Without that, on a standard hardware, so my 8-year-old laptop can maintain a 1 kilohertz real-time loop indefinitely. So I run the preempt RT kernel, but I don't do anything special besides that. Running generic Java with preempt RT. I can maintain kilohertz communication, no problem. Run the preempt RT kernel with the compiled mod. You can go a little bit faster than that. You get about 5 kilohertz before you start processor locking on my machine anyway. But it goes from soft real time, where if it fails, something fails, to hard real time, where if it fails, literally the computer stops. And if you're doing some very hard real-time application, this stack does work for that. And because the way scripts pass data between them is list of object, you have real-time and direct memory access for data transfer. No pass by value like ROS does, you have pass by reference. So the 2 core distinctions between what ROS does and what this is capable of doing is runtime that is real-time without any modification of code, and a guarantee of data transfer being passed by reference, as opposed to having to take your gigabyte point cloud, sending it over a network socket, and then extracting it back out again. Okay? So, who believes me? Let's find out. So, here it is. BowlerStudio runs on Windows, Mac, and Linux. You can run the jar file directly. There's no other sort of system dependencies if you already have Java 8. However, I have installers for your Windows, Mac, and Linux. The first thing that you see is our tutorial. So the tutorial, to begin with, I actually use this to teach programming to children, so the tutorials are a little light at the top level, but it gets heavier as you go deeper. Okay, so you see some description of how this is going to work. You see a little piece of code here. BowlerStudio also sees the piece of code and makes it ready to run.
BowlerStudio.
Oh, try it again.
Welcome to BowlerStudio.
Welcome indeed. So, this is a description of how code is stored. I already said this, we're going to skip that. It supports
Write
closure.
scripts in Flutter.
Closure? Oh, it's like Mary Poppins or something. It's a text-to-speech library that works great, so I bundled it. You can write Python.
You can write scripts in Python.
Python does take a little bit on the startup. The first time you run it, starts up the Python compilation engine and downloads all of the dependent libraries. So the first time you run a Python script, you got a big lag, but it then runs reasonably fast after that. Most recently, we just added Kotlin. Oh, I hit the stop button. No. Try that again.
Write scripts in Kotlin.
And now we get into actually doing something. So here is, if you were to scroll down, you'd see the code down here. But we're just going to run it. So here's a bit of sample code that loads a bunch of the objects in CAD and then one of each of the vitamin types. Pretty fast. Not too bad. Here, let me give you an idea of how many things are there. Lots of things. Okay. Rotate around so we can see all the things. There we go. Now, let's imagine you want to know how this code works. You hit either make a copy if you don't own it, or if you're like me, it says edit right away. And let's put my cursor in the text window. I wonder which line of code was used to create what. My cursor ended up on the line that describes this cube, and then all of the cube objects, the objects that were created from this particular line of code, highlight themselves on the screen. Okay. As we continue on, finds another code, a rounded cube, and the sphere, cylinder, and trapezoid, and so on and so forth. Let's say you want to go the other direction. You see a CAD model, you'd like to know which lines of code were used to create it. Right click, read source, and now all the lines of code from here that were used to create that shape that I just right clicked on highlight themselves. And we can see it if I click here. There's the cube, the sphere, and moving it into place. Okay? Now, let's running low on time. Fast forward. Okay, so up here we have our workspace. This is all the projects that I've been working on recently. You see files. If you hover over the file menu, it'll clone that repo to the disk. Until you hover over files, it won't clone it. You can see the commit history as well as switching branches. The GitHub menu does much the same thing, but it starts off with the organization and then all of the repositories within the organization, and then you get to the files. So you can see why shortcut's a good idea. Okay? You can also simply directly add devices. So the first thing I'm going to do is switch the Wi-Fi over to my special Wi-Fi that I brought, because my cat does not like WPI wireless, but who does? All right, so cat, and then we're going to check and make sure that cat's online by doing a quick rebootski. So this is just the Arduino print terminal, making sure that the cat comes up. All right, got an IP address, living the dream. Bold move, Cotton. Let's see if it plays off. And you simply add your small cat Grace. Dope. Bold move indeed. Look, a software demo and a hardware demo in front of a live audience. It's asking for trouble. All right. Check to see my serial ports. And reboot. Make sure you're on the IP. Hulk IP address. Good. Now, one thing I actually want to show you before I simply disconnect and move on is the fact that it didn't find the hardware. So what did it do? It brought up the configuration and a simulator. So cool. Why not simply simulate our cat? See how it does. Oh, that's what I expected it to do. More or less. We can do turning. We can do walking. But because there's no hardware connected, this is running entirely in simulation. Let's hit our disconnect and see if we can get it to actually connect. That would be really cool if the demo that I just checked would actually work when I'm standing in front of it. Ay, ay, ay. Huh. So you're on Hulk. Are we not on Hulk for some reason? We're not on Hulk. That would be why. Hulk. Connect. Am I going crazy? I did do that before. Thinking about it, thinking about it, thinking about it. Okay, good. And again, connecting and disconnecting, relatively quick. You can load, you can see which devices are loaded, and it prints out in the terminal that it was in simulation mode. So let's try that one more time before I give up. Haha! Being connected to the right Wi-Fi network is important when sending UDP communication packets. The way the device finds, the two halves find each other is the BowlerStudio sends out a UDP broadcast. The cat has an ESP32 in it, but no control logic whatsoever. Just an ESP32 server that has two things. A servo server, where it says, I have these servos, and you can tell me what position to put them in. And it says it has a built-in IMU, and it sends back floating point data of the Euler angle pose of the robot. This is all well and good, but let's make it walk. And since we're not using Solstice, you can actually see that the correspondence between physical reality and simulation is quite good. Oh, right, and I forgot to show you the physics engine. Oh. So, hey, this is cool. Let's simulate in physics. Run. Doop. Now, I've got a JBullet version of... Whoop, 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 whoop. Bold move indeed. A JBullet version and a physical version. So there's the physical crossover. That was the part that I definitely wanted to show. Got a minute or two. Now let's do your development loop in the time we have remaining. Okay, so I'm going to disconnect this robot. Connect a different robot. This one, unlike SmallCat, actually has a fully parametric CAD. The model itself regenerates itself based on the kinematics. So we're going to open up. Where's Carl? Not Cart. Carl the Hexapod. And close, 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 close. So let's take a look at our Carl the Hexapod. Now, Carl the Hexapod is the first model that I made in BowlerStudio, the very first one. And it was made to illustrate the point of doing the full stack. So Carl's got 6 legs, they're splayed out. It's a very simple, obviously these chains are programmatically generated sort of thing. So this has 18 servos. It does the same walking kinematic live generation. Now, let's say we get our design this far, the walking works, the kinematics work, the model's ready to go, and the professor says, that's a cool robot, but here's the thing. I want you to take the first leg, and I want you to move it somewhere. Not entirely sure. I'm going to take this leg, and let's say we want to move it, up in Z by a bit. Just want a little bit higher than the others. And then, of course, because I need that leg to be a little bit higher, I think we're going to also need to go into the elbow and maybe adjust the radius a bit so that foot can still touch the ground. Obviously, we want that to the limb to be able to touch the ground. And okay, let's simulate it. Stuck in the coordinate frame of the limb. We're going to simulate it. Okay, that looks like that'll probably walk. Let's run a physics simulation before we run out of space here. And all right, so there's our new CAD model with the new kinematics ready to roll. Slightly shorter than 8 months, huh? Yeah? All right, so this is the idea that with integrated development environments, you can do this development loop faster. It isn't to say that it does any one of those tasks particularly faster than any other. It is instead to say that the entire system is the thing we're developing, and the system can be developed significantly faster by not having to consistently and regularly context switch between different applications and instead live in a common app. Anyone have any questions? Not that we have a huge amount of time for questions, but I'd be happy. Yes?
What about the library, design library? Is it like very, how do I say, very diverse or something?
You mean the vitamins?
No, the motors and everything. You don't have to design it again and again.
Yeah. So the term that I use is vitamins. Here are all of the types. Within each type, we have different sizes. From micro metal motor, brushless motor, O-rings, lots of VEX stuff, and each one with different sizes. And if you were so inclined as to add an additional one, there's even a wizard for adding vitamins that I haven't already added. It'll add it to your local repo, and it'll send a pull request back to me to add it to the main line so everyone else can have it. Unless, of course, you make your repository private, in which case you can have your privacy if you really, really have to have it for some reason. It's just intentionally out of pipeline. Does that make sense?
We have time for a few more questions. 266.
So it's free and open source. So anyone wants to download it, I'd be happy to help. Yep.
Do you use iterative IK solvers in this?
I don't have an iterative IK solver, but the way the architecture is designed, you can simply slap one in. You simply implement the inverse kinematic interface and tell your mobile base to use your script instead of the default one. It would be arbitrarily easy to add.
How well does it handle like fluid, soft stuff, elastic stuff?
Not yet. I am working on an integrations with a finite element analysis, which will do a little bit of mesh deformation analysis, but at the moment, the stiffnesses are assumed pure stiffness because again, we're dealing with smaller scale 3D printed parts, so for the most part, that's not even a bad assumption for us to make, given the force scales that I mostly deal with this package. And again, you go bigger, there are dedicated packages specifically for that kind of stuff, but not quite yet. Yes?
So you can do all of your development pretty compactly within the environment. How do you export after to be able to run completely independent development for production systems?
That was what I was talking about with the last slide, the headlessness of it. You simply...
How does that work?
You run it from the command line, essentially. You just take the script and run it. There's a jar that you run from the command line, and you just pass it the Git URL and file you'd like to bootstrap the process. So if you have like a launch script, which is this is us running and doing all the things script, you simply call it from the command line with its Git URL location, and the UI never opens. It just runs it with all the underlying systems. No change to your code at all. It's just sort of a different runtime. Yes. Yeah. Most of that will live in the config file versus the code itself, because I try to keep a good isolation between configuration of the robot, the execution run times for standard types of robots, and then the CAD generation that both of which slurp in the configuration file to set themselves up. Data storage is intentionally kept in config files and out of the code itself, but that's more of a convention than a requirement. Strictly speaking, it's code. You do what makes sense for you at that point. This is basically just a bootstrapping runtime for it all. Yes?
Hey, I really liked your presentation.
Thank you.
I don't come from much of a robotics background, so I think I'm probably going to be using BowlerStudio.
Please do.
To learn some of that stuff as fast as possible. But you talked earlier